Hey team, so if you've been following along, maybe you remember that one of the last times we spoke, I tried to convince you that CSV files were the greatest idea of all time. Like, you could define some tabular data, and instead of having to worry about all these hard questions, like why would we store anything in this hard to work with binary format that has to be encoded, it has to be decoded, when we could just use a simple plain text format. Instead of having to worry about all these weird encoding problems, we can just have a simple text-based representation where we store a column of names, a column of aisles, and a series of rows just in a simple CSV format like this. But wait a minute, today I'm going to convince you of just the opposite. I'm going to try and convince you that CSV is one of the worst ideas of all time, and instead we should be using something like SQL. So maybe you were annoyed with all the limitations of using simple text files or CSV files. Like, maybe you didn't like the idea that you could have some data inside of a data.txt file, and then maybe you wanted to update this file, but oh no, you made a very honest, very simple mistake where you tried to put the wrong data type inside of this. And what was the result of that? It deleted the contents of your data.txt. So that's a little bit problematic. Maybe we should be working with a representation that is a little bit more sophisticated so that we can't just accidentally delete our data whenever we make a tiny simple mistake. Or maybe you were annoyed with some of these problems, like where everything was a string. Like, objectively, if we look inside of this turtles.csv file, we see that we have a species, a length, and an age. And it looks like these age fields, like 92 and 30, well, both of those look like they should be some kind of integer represented data. But if we were to actually import CSV, open up this turtles.csv, and look at the result of casting the csv.dictReader object into a list, we would actually see that the result was that these ages were not integers, but these ages were actually strings. Maybe that's a little bit problematic. Maybe it would be really helpful if we could have some kind of representation that stored metadata about what the type of each column was, instead of having to manually convert this every time. Maybe you're even being a little bit forward thinking. So when we only have a very small amount of data, such as 2 rows in a CSV file, maybe it's not that big of a deal. But perhaps you noticed that we had to save and load the entire file every time we were working with this. Like, if we wanted to open up the turtles, we had to open the file, iterate through all of the rows of that, casting it into a list. And then if we wanted to write it back to a file, we had to do the exact same thing in reverse. We had to open the CSV file in write mode, we had to initialize the dictWriter object, we had to write the header, and then we had to write every single row from that list of dictionaries back into a CSV file. So maybe, I hinted at this a second ago, but what if our file was 10 times bigger? What if our file was 100 times bigger? What if turtles.csv contained 100 gigabytes of data? Could you imagine that maybe it's a little bit problematic that we're trying to read 100 gigabytes of data into Python and then write 100 gigabytes of data back to a file? Okay, so these are just some of the motivations behind what we consider the database problem. So a database is really just a tool that gives us some data storage guarantees, it gives us some information about data types, and it even lets us partition our data into logical groups. So many problems that you're going to encounter in the real world are ultimately data storage and data querying problems. And we've actually seen a couple of these in variations so far. So previously, we saw this notion of hierarchical or tree structured data. We also saw this idea about graph structured data. So in the first one, maybe we have just some kind of rooted node where we have a simple hierarchy of objects that kind of extends down like a tree. In the other notion, where we were talking about the World Wide Web or the internet, we were talking about these series of linked nodes. So both of these are really powerful representations, but in fact, the reason that someone named Edgar F. Codd in the 1970s was proposing something called the relational model was actually because of some problems that these two models have when you're actually trying to work with data in the real world. So We're in computing. In computing, things tend to change really, really quickly. There's very few things from like the 1970s that we're still dealing with. But this representation in this model, which we will later call the relational data model, or the just relational model more generally, is something that has pretty much been in continuous use since about the 1970s when it was invented. So today, I want to introduce you to the relational model. We want to talk a little bit about the implementation of the relational model in MariaDB, and we want to talk about the creation and querying of these approaches with something called structured query language, or SQL. One of the last examples we talked about in the CSV chapter was starting to get to this problem where we had things like chicken noodle soup and IL6 that was effectively stored twice because we had to look at it for both Alice and Bob. So the motivation that we want to have when going from tabular to relational data is that there's actually different ways that we can break apart this data such that we're not storing things or duplicating the same information multiple times. So the working example I'm going to have for the next few minutes is that I want you to also imagine that in addition to the idea that we're shopping for Bob and we're shopping for Alice, we may also want to have other information such as Alice's phone number, Alice's street address, so that maybe we know where to actually deliver these groceries eventually. So maybe the first thing you come up with is that we already have Bob, we already have Alice, so maybe we can just add a new column onto our CSV where we just store this data. But if we were noticing a moment ago that we were kind of duplicating some information where we had chicken noodle soup is on aisle 6 multiple times, notice how much information we're duplicating now. So we have all of Bob's information right here. We have all of Alice's information right here. Oh no, but then we also have all of Bob's information again down here. So could you kind of see maybe there's going to be a problem with this? Like, let's imagine that Bob has to change address. And all of a sudden we have 1, 2, 3 places that we have to update Bob's address at. So this is generally called the data normalization problem, where I don't want to get too far into it, but very generally, we want to simplify this representation so that we can get down into the base things that we're actually storing. So really what we're representing right here is that we have 3 different concepts. We have people, we have groceries, and we have the orders that people place. So scrolling down a little bit, the way that we can imagine these is that we really have 3 different pieces of information that we're keeping track of. We have the people, let me try that again. We have the people, we have the groceries that we are shopping for, and we have a connection between these 2 facts, which is the idea that people can order groceries. So the name for these is that each of these pieces, each of these tables, is called a relation. The columns inside of these are considered an attribute on the relation, and if you want to get a little bit technical, the size of the number of columns is considered the relation's arity, such as binary, ternary, etc. But the nice thing about breaking down your data this way is that you can think of it as like these high-level representations and the connections between them. So, for example, a person will place an order, or you can think of an order being placed by a person and then containing a series of groceries. So this decomposition is closely related to what Codd and others called the data normalization problem, but it does require one additional concept. And maybe if I zoom in on this right here. So in order to represent the idea that a person places a grocery order, we have to have some notion of like Alice wants carrots, or Bob wants tea, for instance. So we need some kind of way to connect the people and the groceries. We could do this by just having a very simple representation of like the person's name and the thing that they want. But here's a problem I want you to think about. What if all of a sudden there is a second Alice in the data set? Is it possible that there could be 2 people who are both named Alice, who have different phone numbers and live at different locations, but nonetheless both share the same name, Alice? Well, suddenly if we have that situation, it's really hard to know who we're shopping for. Are we shopping for this Alice or that Alice? If only there was some kind of way that, oh yeah, of course, this was invented at the same time when Codd was inventing this whole relational data notion. So this is the idea of cross-referencing data between 2 relations, But in the original paper from 1970, where Codd was introducing this problem, he also introduced that there was a user-oriented means of fixing this, which he called the keys of a relation. There's two main ones, the primary keys and the foreign keys. So a primary key, which I'll actually kind of jump down to here, a primary key is a piece of information which uniquely identifies every piece of data. A foreign key, by contrast, is a way to reference the keys in another table or another relation. So let's get some practical examples. So in the original person table right here, so person, you could think that we could just make up a number for every single person. So maybe we could arbitrarily choose that Bob is 1. This Alice right here is person number 2. This Alice right here is person number 3. So instead of having remember earlier, we just had Alice in here multiple times. So this was an Alice right here. This was an Alice down here. And instead of having this confusing problem where we could potentially have multiple Alices, we've invented this primary key in the person table, and then we can use it to reference keys in the order table. So this is the core idea between primary and foreign keys. We have a unique piece of data that we either invent or we have from some other implementation, and we can simply use that information later to cross-reference it between tables. So this is the imperfect but nevertheless good enough idea behind normalization. And if you have a database course, I imagine they're probably going to cover normalization more than you really would actually want. But a fully normalized data set is one without redundancy, where every row in a series of relations that can be uniquely identified is uniquely identified. And whenever we need to cross-reference data between any of the two pieces, we can just go through the primary and foreign keys. So normalized data, as we show in the book, is pretty useful. If we need to change something, then we only need to change it in one location, as opposed to that giant CSV we started with, where if we wanted to change a person's address, it would require updating a lot of different rows of data. Okay, so far, this discussion has been pretty much focusing on the concepts and the theory behind it. So, as I mentioned earlier, this was invented in the 1970s as just like a kind of a theoretical way and a bit of a practical way to solve a bunch of the problems that we're dealing with the hierarchical and the graph-based or network format. So now let's get into some of the idea of how do we actually define relations? Where does some of the data come from? How do we add or remove data? In other words, we are ready to interact with an implementation of the theoretical model, which is in the MariaDB database.